result is that the integral over M, where M is compact, dx is volume measure, F has finitely many critical points. So this integral is asymptotically equivalent to 2 pi h to the power n over 2. This is actually quite a remarkable number. In physics, it's frequently referred to as sort of the quantum volume of the phase space. I mean, this combination 2 pi h is rather common in semi-classical quantization. So then the determinant of the second derivative of A at the point A plus I pi over 4, the signature of F2 at A, times the sum over non-trivial graphs with the valency of vertices greater or equal than 3 over the number of elements in the automorphism group of gamma, and then the weight of the graph, and the weight of the graph depends on which critical point you choose, and it's calculated by the matrices of the second derivatives in local coordinates and by high derivatives in local coordinates at the critical point. So these are the weights of edges, or more precisely the inverse of this matrix, and this is the weight of vertices. Now, just in the break, you rightfully noticed that this is all written in local coordinates. And it's actually, it's a non-trivial calculation to check that it doesn't depend on the choice of local coordinates. And of course, it's desirable to write this in terms of jet bundles, but I don't know any good reference where it's being done. But of course, it's probably a very nice exercise. So, okay, so then, now we departing from this simple case where there are isolated simple critical points, and now we have the group acting on M, F and dx are G invariant, and we want to do the same. We want to find the expression for the asymptotical expansion of this integral in terms of final diagonals similar to this. So, before I will do this, I want to kind of make sure that we are on the same page in sort of dealing with Grassmann variables. So, in physics and in gauge systems, it's very important to have so-called fermionic variables, and so let's first discuss Grassmann algebra and integrals over Grassmann algebra. So first, what is a Grassmann algebra? So suppose we have a vector space, so it's a finite dimensional vector space. In this discussion, everything will be over C. Well, since it's over C, it's also over R. I mean, the theory is the same. So the Grassmann algebra generated by the vector space V is simply the exterior algebra of this vector space. The multiplication of monomials is just the exterior product And if we choose a basis, EI in V, then such monomials is a basis, linear basis in the exterior algebra of V. So, Grassmann algebra is simply the way how to define this exterior algebra in terms of generators and relations. So it's rather clear that there is an isomorphism between the exterior algebra and the associative algebra generated by elements EI with defining relations EI EJ plus EJ EI is equal to 0. So in this way, there is no need for new name. This is just the exterior algebra of the vector space V. But if you look at the physics textbooks, you will see the name Grassmann algebra. So this is what is understood by Grassmann algebra. So then there is also a notion of integration over the Grassmann algebra. And the notion requires the orientation of V. So choose an orientation of V. An orientation of V is simply a vector in the top exterior power of V. So, for example, so it's a choice of basis. In this one-dimensional vector space. So an example. We have this element of the basis. And then if you, the only way how we can what we can do is we can permute elements here, so then, of course, everything will be proportional to it. Alright, so once we choose a basis here, then we can define the following. The integral, and I will also use the name Gr(n) for this exterior algebra. So the integral over this Grassmann algebra of an element F. So this is simply the top component of F. So F can be written F top times this element orientation of V plus lower order terms. So this number, by definition, is the result of the integration of this Grassmann algebra. There is also another way to think about Grassmann algebra. So you can also say that these are polynomial functions on the super vector space where the even part of this vector space is trivial, so it's a completely odd n-dimensional vector space. And when I write this, this is the definition of what the polynomial functions on odd vector space are. This is just the exterior power of Cn. So then, in these notations, and again, it depends on who writes this, so sometimes you can see these notations. F, dc, and the usual name for these bases is C. So then the Grassmann n is the algebra generated by Ci some reasons, C, A, or B are usual letters to denote this. So this is really, so this is the top, and that's the definition of all these symbols. So now, why it makes sense to consider such symbols? Mostly for the following reason. Let's look at the analog of the Grassmann integral. So Grassmann-Gaussian integral of dc. And that's the definition. So let's compute this integral. So it's equal to, so by definition, it is equal to top to the coefficient to this element. So let's just find it. This is equal to sum over n greater or equal than 0, 1/2 to the n over n factorial, c dc to the n. And maybe I should write k. N is the dimension. So it's clear that this integral will be 0 if n is odd. If it's an odd dimensional Grassmann algebra. We will never get the top degree monomial here. But if it's even, then among these monomials we will have the monomial c bc to the power n over 2. And this one will be of degree n. Is it clear? So we have an associative algebra generated by elements Ci with the defining relations like this. And we take in this associative algebra the quadratic element like this, and all we do is we just take this power series, and it's clear that all elements of degree larger than n over 2 will be 0, because one of the consequences of this relations is that Ci squared is 0. So if you have any repetitions in such monomial, it will be 0. And if the degree is greater than n over 2, there will be repetition. So it's actually polynomial. And then we are interested in the top coefficient of this polynomial. And let's choose orientation of V to be C1, Cn. So all we have to do is we have to write this as some number that will depend on B times C1. Well, now I will not use the exterior algebra notations, just the notations of the associative algebra with this defining relations. Welcome. So now let's compute this number. We have C I1, BI1, J1, CJ1, CI2, B. In the text, I'm very careful with upper and lower indices because it's actually desirable to have. So then we have n over 2 such things, so it will be n over 2, j n over 2, c j n over 2. And then we take the sum over all I and j. That's the discretization. So now let's just write this as sum over pairs I and j. B I1 J1, B I2 J2, and so on. C I1 C J1, C I2 C J2, and so on. And now let's look at this expression. So altogether there are n elements here. If there is a single repetition in this sequence, the monomial is 0 because c squared is 0. So this sequence I1 J1, I2 J2, and so on, it should be permutation of the sequence 1 through n. So then we can rearrange this monomials in the sequence 1 through n. We will get sum over permutations b minus 1 to sigma, b sigma 1, sigma 2, b sigma 3, sigma 4, b sigma n minus 1, sigma n, times c1, cn. So we obtained the following answer for this coefficient b. It is the sum over permutations sigma minus 1 the sigma, and then this product of these. So you see it's similar, it is similar to the determinant, but it's not the determinant. So then for the integral of this thing, so by definition it's this number, so it's equal to 1/2 to the n over n factorial 1/2 to the n over 2, n over 2 factorial, and then this summation. And there is a special name for this number. The name for this number is the phi-fem of the matrix B. B is the skew-symmetric matrix, and for any skew-symmetric matrix, this number defines the phi-fem, and it's defined for even dimensional matrices only, but we already seen that this integral is 0 when it's an odd dimensional matrix. And there's one more useful formula for the phi-fem, just in the same way as we were discussing yesterday perfect matchings. So you can see that here Well, in the previous discussion, it was not the pattern, the thing that we discussed before, the so-called permanent of this symmetric matrix. When the matrix is Q-symmetric, this combination is called pattern, but you can see that it doesn't depend on. So you see, it's an arrangement of numbers from 1 to n into pairs of numbers: I1, J1, I2, J2, I3, J3, and so on. And now look at this set. If you permute any two pairs, the sign here doesn't change because you're just permuting factors in the commutative product. The signature of the permutation also doesn't change. So actually, this sum doesn't depend on permutations of pairs. If you permute the entries of a pair, one of these b's, the corresponding b, will change sign. But then -1 to the sigma also will change sign. So it doesn't depend on permutations inside. So you can see that another formula for the pattern is sum over perfect matchings. M on the set from 1 to n. And then we can identify M with the equivalence class of a permutation. So it belongs to Sn modulo this S2 to the n over 2 Sn over 2. The permutations inside of pairs and the permutations of pairs. So then we define this as -1 to the sigma. So then B sigma 1, sigma 2. So then that's one right. So B sigma 3, sigma 4, and so on. So we sum over it's a sum. So the sum is taken over perfect matchings. Each perfect matching is considered as the equivalence class of a permutation. So you put any representative of this equivalence class into here, you get this number, and you're summing up these numbers. That's the problem. And so this is the answer for the Gaussian integral over the Grassmann algebra. It is 0 if n is odd, and it's the pattern of B if n is even.
Modulo the factors.
No, you see.
You incorporate the factors.
Yeah, the factors.
They cancel out.
They are already incorporated in the fact that here we're not summing over all permutations, but only on the
Okay, I'm sorry.
only equivalence classes.
Yes.
Okay. Any other questions?
In the sign of the perfect matching isn't well defined, but the function you're writing up there.
No,
is
this is wrong. Yes, that's what I meant.
This is well defined by the
this,
argument.
yeah, this is. So if you want, you can write this as the product of the absolute values of b's corresponding to the perfect matching, and then some sign that's defined.
Actually, pattern anyway square root of the determinant, right?
We're coming to this.
Yeah.
So yes. So now we have the. So this is essentially what I did now is the following. Suppose that so let's take a vector space V. Suppose you have the element B, or let's say B in V wedge V. In the basis, you can write it as Bij EI which EJ. So then in the exterior algebra you can take top exterior power of this element B. Right? So then this is equal to the pfn of B times the U1. That's completely equivalent state. Okay, so now yes, so now let's so there was this remark about the square root of the determinant. So let's put this in the context. It's so in order to see this, so the statement is that pfn square is the determinant. Well, actually there are two important properties. That's the first one, and then the second one is when you have pfn of the matrix which is skew-symmetric but has this very special block structure, this is equal to the determinant of A. So so I will leave this identity to prove this identity as an exercise.
Probably you just need it for a few basic kinds of matrices. You need it for this kind and for diagonal ones.
All I need is this.
Yeah, and then conjugation invariance or something like this, and then density or something of the invertible. To show this, just to show this identity, probably one can get by with just this. I mean, just this equation here plus some conjugation and some density of the invertible matrices and all matrices.
No, it's easier than this. It's just exterior algebra.
Yeah.
It's just
of course, but yeah.
But you can choose it in any basis. That doesn't depend on the basis, so you can choose a good basis.
Right. That's what I'm saying.
Inversibility is not.
Maybe not an issue.
Well, if it's not invertible, no, it's the identity 0 is equal to 0.
Then you need to know the other one.
So let me first prove this one. So let's assume that V is equal to W plus W0. And the matrix B has this form. 0, A, and then minus the dual operator. So A acts from W to W dual. A dual acts from W dual to W. So then, just if you look at this formula, so then how to choose the orientation? So let's choose a basis here, E1, En. Here we have the dual basis, E1, En. So let's choose the orientation on W to be E1, En, and the orientation on V to be E1, En, E1, En. So what's the property of the determinant? Well, the property of the determinant is if you have an element A, which is somewhere Aij, say Aij EI tensor E J. Well, it's a little bit of a mess with the upper and lower indices, but that's just a little bit. So then from 1 to n. So then A to the n is the determinant of A, I mean the top exterior of En.
Then A is a linear map from V, from W to W.
Yes, and I don't, well,
No.
I'm very tempted to leave this as an exercise. This is the tensor product, of course.
Actually, A is actually from W to W, and they start from W start to W start.
No, you don't mean, you mean wedge, not tensor product, don't you?
Yes, you do. That's right, wedge.
Yeah.
What?
You don't mean tensor product. You mean wedge.
The one side, the spaces are different, the wedge is, the tensor is the same.
Well,
Yes, so I think it's a tensor product.
It should be stars.
Not. Because one lies in how, I mean, wedges makes sense when you talk about the entire
It's
space.
symmetrization.
Yeah.
So is this what I mean?
No, there should be one star in each line, right?
I thought so.
Because it's often diagonal.
Why don't you just
When
leave this as an
when you write out the
exercise?
matrix, you should have like the dual of the dual basis. So it's actually should be lower in this quadrant.
That's what I thought.
Anyway, just make it an exercise, huh?
Yes,
That's
that's
why
what
you make it can be done without learning algebra. You just substitute in the form of a fraction.
Yes, but it's much better. It's much better to see it in terms of linear algebra. So, this is homework 1, and this is homework 2.
Maybe we can quote Graham Siegel and say some exercises are best done in practice.
I completely agree. So, okay, so this is, so at least that's the idea how to do this exercise. So you just take the top exterior element corresponding to this bilinear form in this space, and then you will see that it's the determinant. So now the way now the way to phrase it in terms of the these Grassmann integrals is the following. So now we can take the integral over say a b. So now we have, and we're taking the integral over c 0n dA dB, and that's equal to the determinant of A so that is equivalent to this statement, because you can write AB as 1/2 CBC, where C1 through C2n is A1 AN, B1 BN, and the matrix B has this form. No, it's the 2n by 2n matrix, and that's more or less the proof of this statement. So, so this is really what I will use. But then there is a so this is the Gaussian. These are the two Gaussian integrals that are extremely important. But then there is an analog of Feynman diagrams for Grassmann integration. And this is the following. So now there are two versions. One is for A and B, and it's customary to denote B, say A as B1. That's the usual notation. But it doesn't mean that it's complex conjugate, it just means that it's another set of independent Grassmann variables. So, theorem is that if you take this Gaussian part, and if you add here the polynomial in C, do the same thing, integrate over C, meaning that you take this expression in the algebra generated by C and you take its top exterior power, top exterior component. So then this is equal to here, minus B, and then 1 plus sum over gamma, minus 1 to the C of D of gamma, divided by the number of elements in the automorphism group of gamma, and then F of D of gamma, where D of gamma is a diagram of gamma on R2. So just the way how we draw the diagram on R2, C of D of gamma is the number of intersection of edges of gamma, so the measure of non-planarity of gamma.
This C has nothing to do with that C. Too many C's.
Pardon?
You have, maybe you could denote that not by C.
Which, no, this number is this number.
Yeah, but just the letter C is over here. That's the
Ah! Oh, you mean with that C?
yeah. Of course it's different.
Yes.
I of
Yeah.
intersection.
Well, no. It's terrible, I mean.
I can. So, F of D of gamma is the weight, and it's computed in the same way as before. So if you have a trivalent vertex, then you put the weight, so P is the polynomial of degree at least 3, so it's sum over n greater or equal k greater or equal than 0, then 3, 1 over k factorial, and then sum over I1 ik, p I1 ik, c I1, c ik. The difference with the previous case, with the usual integral, is that these coefficients are skew-symmetric. So when you draw a diagram, well, it's so there's a yeah, you should choose a total ordering of vertices. So then it's P1, I1, I3, and then the weight of the edge is minus B inverse Ij. And notice that all these things are skew-symmetric. So when you change the projection, when you change the embedding of, well, it's not an embedding. So if when you change the projection of gamma to mapping of gamma to R2, then you may change the order of edges. You change the number of intersections, but the total sign will be the same. So the total sign doesn't depend on the diagram, but the sign of this part and the sign of this part. It depends on how you map graph to the plane. So there is another way to phrase these signs. We will come to this.
Well, you need to choose total ordering at every vertex.
Total ordering at every vertex.
So you have 2 degrees of freedom: embedding in the plane and total ordering.
But
And you claim that it doesn't depend on both.
Or, well, given the projection, you have a total ordering.
well, you have a total ordering as to. I mean, you have a cyclic ordering determined by the orientational plane.
Yeah, and total ordering should agree with it.
Yeah. Yeah. Okay, so how to prove this statement? It's a straightforward exercise.
Number 3.
Hmm?
Number 3.
Well, let me start at least. So it's based on the following lemma. Remember, in the bosonic case, we started with the integration of monomials. So the same here. If you compute this integral, where this is k, and we have n fermions, meaning that it's a 0 n-dimensional supervector space, the integral is taken in the same sense as before. So then it will be 0 if k is odd, and it will be the pfn of minus b times the. So now I should remember the signs. So minus 1 to the power k root 2. And then the pfn of the matrix, well, I'll just write it explicitly as sum over perfect meshings. Again, minus 1 to the sigma representing m. So here meshing is the equivalence class of sigma. And here we will have the following entries. B inverse sigma 1, sigma 2, B inverse sigma 3, sigma 4, B inverse sigma n minus 1, sigma n. So, in other words, the expression that we have here is the pfn of
It's not m, it's k.
k. Yes, correct. K, where sigma is the permutation of this on this set, and I assume here that i's are ordered in this way. So in other words, this is the pfn of the matrix B minus 1 IAJB, A and B are from 1 to K. I, A, I, B. You take this set, so it's the K by K matrix where the entries are enumerated by this indices. Right, so, and then I'll just outline the proof, and then you just expand this integral in just as before, in powers of p, in powers of every monomial in p. Use this lemma, use the same representation of diagrams as by perfect meshings as I did before. And then the only difference will be that at every intersection here you will have an extra minus sign because here we used Pfeffens, not permanents, because there is this extra sign minus 1 to the permutation. So every entry here will contribute as a minus 1 in minus 1 to the signature of the permutation. So this is the formula for this fermionic integral. Any questions about this? No. Yes, the question is clear. So we have to make a break.